Before we actually move on to examples and the things that we'll see today, I wanted to make sure that we are all on the same page on some of the basic principles. So I've listed a few potential questions here with the hope that if there is anything that you're not very familiar with on this list, you would raise your hand and ask any questions you want. And so as we said, this part might be edited out, so there's no reason not to ask any questions. So the first concept that will be important for what we'll talk about today is what the likelihood function is. So the likelihood function is the probability of some observable x given some parameters theta. And in most cases that you will see in practice, people use very simple assumptions for what the form of this likelihood is. And they, for instance, assume it to be a Gaussian. And so, for instance, in typical cosmological model, it would look like this. You have a mean function that depends on some parameter theta, and you have some covariance here. And those are the two elements that you need to define this probability function, and that's your likelihood function. Any questions on the likelihood? For instance, do people know? For instance, why didn't I put theta here on sigma? Anyone? The cosmologist in the room. Is this a good assumption to make?
It's good assumption to consider a cosmologically independent covariance so that you don't double count the information that you might have in your cosmological models.
Right. So exactly. So here we are making the assumption that the covariance matrix doesn't depend on cosmology, or at least we keep it fixed. And then this probability function only depends on the mean of your signal that is given by your theoretical model. So for instance, in some of Virginia's project, where Virginia, you look at potentially non-Gaussian statistic, this distribution, this assumption of using a Gaussian may not always hold, right? And so you have, when you design your model, you have the freedom of choosing any distribution you like. If it's given, if it comes from theory, you have some certainty that it can be the right distribution, but you can also make mistakes here. And you can, for instance, assume a Gaussian when your real probability is not a Gaussian, and then that will cause problem further down. Right, so that's your likelihood function. As I said, either given by theory or you need to assume one for whatever purpose that you have. But the whole goal of this function is just to give you a probability of some data given some parameters. All right.
I have a question here.
Yes, go ahead.
Is it possible to have more than just mu and sigma in your n function as a parameter?
Right. So n here is just a symbol for Gaussian, normal distributed. So that's just a distribution function. But you could imagine that your likelihood function is actually a lot more complicated than that. It can be a combination of several distributions. There is no limit on how complex you can make it. So, okay. For instance, I mean, you could imagine. So we would depart a little bit from what we do in cosmology usually, but for instance, you could imagine that the mean of your signal is given by one parameter, and the covariance of your signal is given by another parameter. And then your likelihood function is now different. It's a Gaussian, but it's more complex. Yeah, it's parameters that come in different places. That's valid.
Okay.
All right. So if we have a function that tells, rather a distribution that tells us the probability of observables given parameters, one thing you can do with that is trying to find the maximum likelihood estimate. So the maximum likelihood estimate is trying to find the set of parameters theta that just maximizes this distribution. Does that make sense? So I have an observed x, right? And I just want to find the parameter theta that, so that my observed X is maximally probable under my likelihood function assumption. So essentially, this is exactly what you do when you fit a curve. You find the parameters of the slope and amplitude that make your data maximally probable under your model. So that's the maximum likelihood estimate. Any questions on that? Okay. So the MLE is good, but here it's just telling you how well your model is fitted to the data. It doesn't tell you if the parameters that you end up obtaining, like the theta parameters, if they are sensible or not sensible. So, and it doesn't give you a probability function over those parameters. It just gives you the best fit value of those parameters. So that's where Bayes formula comes in. So it's a way to, instead of accessing just the probability of the data given parameters, it's asking a way to access the posterior probability, which is just asking the question the other way around. What is the probability of some parameters given my data? And so Bayes formula in a simpler form, it simply looks like this. It's just saying that I can rewrite the probability of some parameters given my data as the product of this likelihood function that we've already defined and a prior distribution. And the prior is, for instance, how I can embed my knowledge that some values of parameters are more likely than others, even before I look at any data. Is that clear? Is that trivial?
I have a question here.
Yeah.
So your likelihood is the model of your errors on what you're trying to fit, for example.
Yeah, yeah.
And the p theta is the actual fitting function.
P theta. So let's say I just want to fit a line. So just a slope and an overall position. P theta is, for instance, the allowed range of slopes and amplitude that I want to allow for my fitting.
Oh yeah, okay, yeah.
So what that means is that if I don't have P theta, any value of theta that ends up fitting the data is fine. But if I have some P theta here, I'm saying I'm going to weight my likelihood function with another function that tells me, if it's all the same for you, I would rather you putting the parameter here as long as it fits the data as well, instead of there, for instance. So it's just a weighting of the likelihood function with your prior knowledge of where you think theta should be.
Okay.
All right. So anyway, the idea is that now we have access to this guy. And so that guy is the probability of parameters given the data. And so that embeds how well a given set of parameters fits the data and how likely we think those parameters are in, just in general. So now that we have access to this distribution, we can use it in different ways. One way that we can use it is looking at the maximum a posteriori solution. So this is just like the MLE. We're trying to find the parameters that are maximally probable, but this time under this posterior distribution instead of just the likelihood distribution. So I'm just taking this here, I'm putting this here. And so now I'm going to search over all parameter theta that may fit my data, but they also need to be probable under the prior. So what that means is that if you have many different possible thetas that are possible, your prior here is going to help you find the one that you actually want and reject the one that you think are completely stupid. Any questions here? All right. And so so that, just like the MLE, will just give me a point estimate. But you can go one step further and you can try to estimate this entire probability distribution function. And so for that, there are a set of tools that we'll call Markov chain Monte Carlo tools. Essentially, it's a way to take samples from that distribution. So the way it works, there are several methods, but generally the way they work is that you start from a given point in parameter space, and you take random steps in random directions, but you are always more likely to go in a direction where you become more likely under the prior. And so you let it, iterate and walk around for a long time, and then at the end of the day, it will stagnate around the posterior distribution. So that's why one way you can use to estimate this posterior distribution. So instead of having just a value, you have a full set of possible values. All right, any questions on any of this before we move on to the example?
What do you do if your likelihood is bimodal?
So if my likelihood is bimodal, so one thing, for instance, is that my posterior may not be bimodal. Maybe my prior is rejecting one of the regions where my likelihood picks, right? So maybe under the likelihood, I have two possible parameters that fits the data just as well. But now that I weight my two parameters by this additional prior, maybe only one remains. But in general, if the posterior is bimodal, then this will be, kind of meaningless. You'll find one value, but it will usually be, a local maximum, and then you may have many other maxima around it. So that's not a good way to summarize your posterior. If you have a good sampler, you might be able to get samples from all of those, minima or maxima, all of these regions. And so you'll have you'll get samples from this multimodal distribution.
And is there a way to know the shape of your distribution without doing a Markov chain?
No. No easy way.
Yeah. Okay.
So one way you can do, for instance, with just a maximum a posteriori, you can. So this is just a minimization problem. So you can start from a bunch of different starting points, your minimization problem, and then they will fall under the local minima, right? So that you will see if they all converge to the same point, you'll be like, okay, I'm fairly confident I only have one peak in my posterior distribution. But if they end up in different places, you'll know that you have different modes. All right, any last questions before we move on to the fun stuff? Cool. All right, so now let's have a look at the real life example. So if I don't have any questions, I'm assuming everybody understands everything, and then there will be zero surprises in the example that we're going to run. We'll see. So for the rest of this notebook, I would ask you not to skip forward too much, because we'll stop and try to answer some questions as they come up as we do the example. So let's get started. So here, what we're going to do is that this is an example that I've stolen from one of Dan Forman-Zmaki's tutorial, and it's simulating some sort of transient event, so in this case, it's a simple model for planetary transit event. So here, those points, for instance, could be the flux you observe from a star somewhere in the galaxy. And then at some point, you observe a dip in the flux coming from that star. And so that is one way you can use to detect that something just passed just in front of the star, and that can be a planet, for instance. So for instance, this is one way that you can detect the presence of a planet. Right. So I've hidden in this cell here the code that generates this data. You don't have to look at it for now, but you can run this cell, and this will give you this. So looking at this data, the thing that you might want to do when you analyze something like this is, I want to find out at what time is the event, and how long did the event take, and how big was the dip in amplitude. So all of this is telling me about, for instance, the size of the planet, the orbit of the planet, and stuff like that. So these are parameters that we might want to estimate. Any questions? All right, so that's our data. And now we are going to try to interpret that data. So for this, we're going to need to build a model. So as I said, the thing that we want to do is characterizing the location, duration, and amplitude of this dip in the light curve. So for this, we're going to use a simple model that I've written here in Python, because I think everybody knows how to read Python. And let's look at the different terms that we have here. So we see that it's a model that depends on several parameters, n, b, amplitude, location, and log sigma value. All right, so what is this b parameter, for instance? Can anyone tell me? What is this m parameter here? Can anyone recognize any of those terms in this equation?
Isn't it b the magnitude of the star, something like that?
Yeah, exactly. So b is a constant. So I should have said t is the time, right? And here we see that in this model that is supposed to model the flux from this observation, b is a constant. So that gives us the overall, the 0 point. So the overall brightness from the star as a constant. Cool, okay. What about that term now?
In the case, it's a variable star to have the variation proper to the star and not to the transit itself.
Yeah, exactly. So maybe we did our subtraction wrong. So maybe, there is some sort of slope in the light curve of the star, and we are going to model it with just a very simple linear model. So that will be our background. So that's just to model what should the amplitude of the light coming from the star be at a function of time. And then we have this guy. So
sorry, when you say overall amplitude, you mean the absolute amplitude?
So the value of the flux,
one.
Right. So we're just no. I mean so for instance, these points are flux values, right, coming from the star. If we didn't have an event here, you can see that it kind of looks like that. It kind of looks like there is a line here, right? So in the absence of an event, what would have been the flux as a function of time from the star? And we're just modeling as a line. Does that make sense?
Yeah.
All right. And so now we model, in addition, just the dip in the light curve. And we are going to model it as something that has an amplitude, that has a Gaussian shape, and is parameterized by a location and a width, essentially. So you can, if you look at this curve, this makes sense. We are going to try to fit this dip as just a Gaussian with a given location and amplitude and width. Any questions on this model then?
Is there a reason to use the log sigma instead of just sigma?
It ends up being more stable in some situations. So for instance, log sigma is unbounded. It's an unbounded value between minus infinity and plus infinity, but sigma is positive, right? So it can mess with your optimization or sampling schemes.
But could you, instead of putting it in your model, having this parameterization in the sampler or in the prior, for example?
Yeah.
Okay.
You could. It's just a choice. All right. So I'm gonna run this, and so that defines the mean of our signal. But as we said in the first step of this tutorial, is that we also need to model the uncertainties. So any recommendations here for what we should do about the uncertainties on this model light curve? Like, what distribution could we use?
Gaussian.
Yes, that was an easy one. So we can use a Gaussian. What should be the covariance matrix for this Gaussian, since we say that a Gaussian depends on covariance matrix? So if I look at my data, I see that I have error bars here, right? And so those error bars are like the error bars that are giving me by the pipeline. When I get a flux measurement, I also get a standard deviation on that flux measurement. So we can use that as a way to build our likelihood function. So let's have a look at what's hidden in this cell. We're going to use a Gaussian likelihood. Good point. And because, why not? We're going to use diagonal covariance. So what that means is that the errors on each point are not correlated. They are independent, right? And they are set by the measurement errors. If we choose that model for the noise covariance, then the likelihood, or the log likelihood, so the log likelihood is just a log probability. You can write it down just like this if you remember what the likelihood for a Gaussian is. It's just you take the model that gives you the mean, and you divide by the covariance. In this case, it's a diagonal covariance. So it takes this very simple formula shape here. Any questions here for how to compute the log likelihood of a Gaussian with diagonal covariance? Any concerns at this point? One question someone may ask is, why are you assuming a diagonal Gaussian covariance? Because here I look at this data, but I know nothing about this data. So I just made a design choice. I just assumed that was the right model to use. And let's see what happens. Okay, so I've defined my likelihood function in terms of its log likelihood. And now if I want to do Bayesian inference, I still need to set up a prior. So one way that you can set up a prior, for instance, with MC, is just defining a function that returns the log value, the log probability for a given set of parameters. So this function takes just the parameters of the model. So you recognize M, B, amplitude, location, and width of the dip. And it returns a value, either 0 or infinity. 0 if the parameters are in given ranges. So that means I'm going to assume a flat prior. So if you are within the region that is allowed by the prior, you can do whatever you want. I'm not going to weight the parameter more than in one way or the other. But if you go outside of this prior region, I'm going to reject it. I'm going to say this is completely forbidden. So that's why we have sharp transition between 0 and infinity. Any questions here?
Yeah, I have a question.
Yes.
Is it, so the way that it's set up, and just because the probability is infinity, from looking at it, it looks like you cannot get an answer that is outside of the parameter space that you've specified. But I have used MC before. I used it in a particularly weird scenario, so maybe it's my fault, and it gave me a value that was outside a parameter space, so that the parameter I was looking for didn't actually exist. And that's what I was trying to break MC. I was trying to use it to tell me that my model was wrong. So I was getting it to search for a parameter. What I wanted it to do was pick somewhere at the edge of parameter space, give me massive errors, essentially fall over. But what it did do that surprised me was it picked a value outside of my parameter space, gave me massive errors, fell over. So it showed me that the model was bad, but what I didn't expect was that it left parameter space, and I thought it really couldn't do that. I thought it had to pick whatever terrible thing inside parameter space.
Yeah, so in principle, that should be the case. Then the only reason why this would have happened is either maybe you parameterize one parameter and then the prior was like on some transform parameter on the same parameters, or maybe in the way you wrote the model, or maybe it's hidden somewhere in MC, because you always have to handle the edge cases with infinity. So infinities are bad, and depending on how they are handled inside the code itself, maybe something happened and it allowed something to jump, but that shouldn't have happened. So it's either a bug or a problem in the problem statement.
Okay, and more generally, is it reasonable to use these sorts of methods to do what I did, or is it unreasonable to do what I did? So I gave it a fake parameter and I wanted it to spot that parameter wasn't real by breaking. Is that just a silly idea to start off with? Maybe that's more a question.
So it cannot break, but what might happen is that your parameter ends up being condensed in one side of the allowed parameter range, right?
Well, yeah, so I wanted to see just sort of a wide distribution across the possible, so it wasn't sort of sharply honed in on something, and it did show me that, but then it also fell out of parameter space. So
yeah, so
I don't know, would you consider that to be a reasonable argument? If I was trying to convince you of a model and I went, look, I've done a null test, this is what I've done, would you be like, no, that's a bit weird?
No, yeah.
Okay.
Yeah.
Right.
So
that's what I wanted to
yeah, that's probably
I would also just think there is a bug in the code.
Yeah, well, maybe you can write to Dan to say, well, I managed to escape from a prior region.
Okay, all right, thank you.
All right, okay, so what we do here in this final function is that now we have our prior that defines our belief that parameters need to be in a given range. And here we just return a function that gives the log probability, the log posterior, essentially. So the value of this guy, which is just summing the log of the likelihood and the log of the prior. I'm gonna get back to that. Right, okay. And so now given this function that is able to evaluate the log posterior of your model at any given point in parameter space, given the data, we can give that function to MC and ask it to run an MCMC chain for us. So get samples from the posterior distribution. So I'm gonna start it, and I'm gonna ask if you guys have any questions here about what's going on in this part.
I just have a question on the previous cell. Why did you choose -infinity and 0?
It's just so that's just a way to write down a uniform prior within sharp ranges, within given finite ranges, let's say. So
if you had, for example, I don't know, for M, you want the parameter to be within a Gaussian, it will be totally different to the value that you've set here.
Yes, so exactly. So for instance, if M, right, well, let's you know, we can do it. If I want M to be centered around 0, for instance, I could do something like log P of M equals something similar to this, -0. So that's close to the log likelihood of a Gaussian, right, centered in 0 with standard deviation of 1. And then here, if I assume priors for everything here, and here I can return, for instance, log M, because the log PM. Does that make sense? I'm gonna remove that. Boop, boop, boop. Right. So now what I'm saying is that for those parameters, if they are outside of the range, this set of parameters is rejected, whatever happens. But if it's within this range, then I'm going to say the value of the prior only depends on the value of M, and I'm going to center that around M equals 0, and I'm going to return that value. Does that make sense? Maybe.
Yeah.
All right. So in any case, so we can discuss more about how you would define other priors, but the thing that I want to show you afterwards is that all of this, defining functions by hand and defining log probabilities and stuff like that is from the past, and we shouldn't do that anymore. And I'm going to show you the 2020 way of doing it just after that. So I don't want to spend too much time on this function.
It was just because the way I'm seeing it, it looks like just kind of flagging, like if the parameters in range, it's fine, so, and if it's not, you just reject it.
Exactly.
But the way a flag will work in my mind will be like, if it's in the flag inside the range, you return 1, and outside you return 0. But here you have 0 and -infinity, which is just way beyond my expectation, I would say.
Yeah, but so infinity is a stupid value, but it depends on how the sampler understands infinity. So if it, you know, it runs the MCMC chain, and then it tries to propose a new point. And it tries to evaluate this log probability function at that new point. And if it falls outside this range, my function here is going to return infinity. And so my sampler is like, here it says that I have a -infinity value over there. I'm going to say, whoa, 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 no. And I'm going to just reject that point and not take the step in that direction. Then I'm going to try to take a new step in another direction, and probably won't be infinity in that direction, and I will go there. So internally, you can think of this as being a flag for the sampler.
Okay, okay. So it's just the way the sampler is working that you choose these values.
Right. But in principle, that's the proper probability for log. I mean, minus infinity is just it's the log it's a log probability, right? So minus infinity means that the probability is 0. The probability of this parameter outside of range is 0.
Okay.
Okay. All right. So, oops. Well, let's see if that works. I don't know. So now I can run MC. So it runs those chains, and I get samples from those chains. So I can look at them. So for instance, here I see that outside of the sampler, I receive 30,000 samples with 5 parameters, and those 5 parameters are the 5 parameters that we have in our model. And I can do stuff like plotting and comparing. You know, for these parameters that come out of the chain, comparing them to my data. So here is what it looks like. I take 24 set of parameters out of my chain, and I look at the fitted value. I mean, at the value of the light curve for this. And what do you guys think? Does that look good? Does that look okay?
Looks okay to me.
But is it though? All right, so yeah, it looks fine. We see that there is a slope, and it looks like the data is telling us that there should be a slope, right? So, oh, good. So now we can do the next step. If you do Bayesian inference, you want to look at the posterior values for the parameters you are interested in. And so here is how, if you run this cell, this is how this will look like with MC. And this control function. And so the plot that I'm seeing here, the dots are a sample from my posterior distribution, and the blue points are values for the true model that I know is correct because this comes from a simulation, right? So the question that I have is, why on earth is my true model 3 sigma away from the maximum of the posterior distribution? Can anyone guess what happened?
You didn't estimate your errors properly?
Yes. Yeah, so exactly. At what level did we mess up precisely? So it has to do with something that we yeah.
The covariance maybe?
Yes, the covariance matrix. So we've assumed a diagonal covariance matrix. We've assumed that the errors that we measure on each point are independent from point to point. And so it looks like we have a lot of confidence in our fit from looking at that. But what we're underestimating here is that those points are actually extremely correlated with each other. So for instance, if one is above a value here, actually all of those are just a random fluctuation above the 0 value. And so here, it looks like there is a slope, but maybe there is no slope. Maybe it's just because there is, all of those points are actually just like, essentially just one point, and it's just randomly slightly higher than it should be. And so maybe there is no indication for a slope here. Does that make any sense?
So why it has to be a correlation between the points and not just that you underestimate the error bars? Or the error bars are just badly estimated directly on the...
It could also be. Yeah, it could also be that the error bars are badly estimated. So right now we've just assumed that we knew perfectly the values from the errors given by the pipeline, but maybe there is an uncertainty in there, and maybe what we're seeing here is that we've, not modeled them correctly.
Okay.
All right, so this is a little bit messed up. So let's try to understand what happened. And maybe we should have worried about covariance, indeed. So as part of what our model is generating the data is providing us, we've asked it to also generate or give us the covariance matrix for these observations. And so here is what this covariance matrix looks like. So what we're seeing here is that there is a little bit on the diagonal. So that means that marginally the errors are more or less independent for each given point. But there is a lot of cross correlations between different points. So you know, like the reason why this point, I mean, this part of the matrix here is bright, it means that there's a lot of correlation between the point at timestamp 35 and the point at timestamp 25. So that means that all these points are not independent but tightly correlated. Any questions on the interpretation of this covariance matrix, or what it is, or anything like that?
Is there a way to quantify the importance of the correlation? Because sometimes you might say, okay, so the correlation terms are pretty low, so I can ignore them. So how is it possible to do it? And
yes.
If so, how?
Yes. So this is beyond the scope of this tutorial, but you can try to model your uncertainty on the covariance matrix. And you can try to fit the covariance matrix at the same time as you fit the rest of the parameters.
Okay.
Does it make sense? And so for this, you would typically use Gaussian processes, but we can have a tutorial on Gaussian processes next time. All right, so what we've messed up here is that we've assumed the diagonal covariance, and that had very bad effects. We actually completely missed the true parameter value. So I'm gonna just undo the changes that I made here, because otherwise I don't know what will happen. Right, and just rerun this. Okay, so we'll try to improve our model. So if we say that now we not only have the value of the errors, but we also have the full covariance matrix for observations. So in practice, it would be difficult to get from whatever your pipeline or something. But as I said, either you can try to fit it from data itself with Gaussian processes, or you have another way to estimate it. So in cosmology, for instance, we'll run cosmological simulations, for instance, to try to estimate this covariance matrix offline. And then we can use it in our likelihood function. Right, so here is the real covariance that we should have used for modeling. And so we can use this covariance to define a proper Gaussian likelihood function, and this time no longer with diagonal covariance. So here is what this would look like. Here, the P means the precision matrix, so the inverse of the covariance. I'm taking the residuals between my model and the data, and I'm evaluating the likelihood of this data given the model just by doing X transpose precision matrix X. So that just weighting the difference between model and observations by the precision matrix, which is just the inverse of the covariance matrix. Any questions on that?
Yeah, actually, sorry, I didn't understand where you took the new covariance matrix.
So the covariance matrix is given by me by the simulation here. I know it because I generated the data.
You took it. Okay.
So I assume that I know the covariance matrix here. In practice, sometimes you do, sometimes you don't. But here, let's say you know it. So if I know it, I can write down the proper likelihood that takes the full covariance into account through the precision matrix. So I define my new likelihood function. I define my new log posterior value, which now just sums this likelihood with the same prior as before. And I can run MC again. And so here I'm running MC. The only difference is that I'm using this new log posterior that takes into account my new likelihood function. And I'm also providing the inverse of the covariance matrix, which will be this P value here. And I run the sampler. Boop, boop, boop. Oh boy. Wow. Is that good? Anyone want to take a guess if this is an improvement or not compared to before?
Maybe you're missing some point to see if there is a tendance. I mean,
so for instance, like that curve, comes from the posterior, but it looks like it's not fitting any data point. Is that, did I mess up?
Well, the way I see it is that it might be just one value that you take for the model, well, bad, but maybe if you look at the entire sampling, there might be the right value somewhere that is chosen.
Right. Okay. That. Yeah. Okay. So I can so every time I run this cell, I actually select new samples from the posterior. So I can run it again, and I will get various possible fits to the data as given by my posterior. So I see that all the time, I have this huge uncertainty here that I didn't have before. If I look back at my fit that I had before, it was super tight, right? And so there's actually nothing.
Can I ask?
Yes.
I didn't understand that what are you plotting exactly? Are you plotting all the posterior distribution?
I'm taking a sample of parameters from my posterior distribution, and I'm running it forward in my model, and so that gives me a light curve. So I've inferred the posterior, right? I take one possible value from this posterior, and I run the model at that value. Does that make sense?
But you're plotting all the ones that you get, or the ones that correspond to?
Oh yeah, so all the
parameter space that are
exactly,
actually
exactly. So all the ones that I see here are ones that are compatible with the data. I mean, that are from my posterior.
Ah, okay.
And yet it looks like it doesn't fit the data, but actually it does fit the data. It's just that all these data points are extremely correlated, which means that it looks like we have 10 points, but in fact we have like 2 or 3 points effectively. And so despite the fact that the error bars on each measurement seem to be small, because they are all correlated, there is actually a huge uncertainty on what is the actual amplitude, for instance, of just the mean value. Because this is essentially just having just 1 or 2 points to estimate this linear background that we had before. Does that make sense? And so I can have a look at my posterior contours now, and I see that there is improvement if I compare the values of the range of those parameters. They are much bigger than I had before, but now they encapsulate the real value at something like 1 sigma, 2 sigma probability. So do you guys have questions or comments at this point?
I'm actually really confused because
okay.
I understand the effect of correlation, but then for me, the error bars that you have on your data doesn't have any sense at all, because
yes, so that's good that you ask, because this comes from what happens when you use real data. So when you use real data, you get this catalog of fluxes with values for each of these fluxes. But what you're forgetting about is that there is a huge chain of data processing that happens before that point. And so this data processing may accidentally, or in practice, correlate all of these points together in a way that you won't be able to see just by looking at the individual uncertainties on the flux measurements.
Yeah,
for instance, let's say you want to subtract the background of an image and then make a flux measurement for the value. So the pipeline will give you the magnitude for galaxy and the error on that magnitude, but maybe forgetting about the errors in that measurement that come from your uncertainty on the background.
But that means that the errors were,
that means that you
propagated properly.
That means that you always should think about the errors that you get in the data.
Yeah.
You get.
Yeah, of course. But because the thing is, when you look at this this plot, is for me it's crazy to say that a curve that is way outside your error bars are better than a curve that's go inside. For me, it's either you're saying something wrong or your error bars doesn't make sense at all.
So okay, it's if the error bars here are point-wise error bars, and they're just showing you the diagonal of this covariance matrix. And that's what you will see on, usually like any data that you'll see, for instance, you look at the power spectrum or measurements of the power spectrum, you'll get, like the error bars on each point. But what you don't see on that plot is that this point may be correlated with each other. So if the bins are large enough, there is not much correlation between points, and they may actually be independent, but they may actually also be very correlated. So the covariance, understanding the covariance of your measurements is an important point, is the point. And when you look at a plot like this, that doesn't tell you about the covariance between points, only about the uncertainty on the diagonal of the covariance.
Yeah, because, well, if you don't know about the covariance and you look at this plot, you just say, well, I don't know who did the fit, but it was pretty bad. So. Right.
So, okay. And so now there is one last question. So this is better because now our true parameters are not completely rejected, right? But then why are my true parameter for this transient event not on top of my posterior? Why do I have this offset?
Maybe the model is more complex than we thought at the beginning.
The model is wrong, yes, is the answer. Something is wrong with the model. I mean, not wrong, but it's model misspecification is the answer. So what happens when you do Bayesian analysis, if the model that you're assuming when you infer your parameters is the same as the one that you generated the data with, then you'll find the answer right on top. But if the model that you use to analyze the data is not the same as the one that actually generated the data, you'll get this type of result or behavior like this. So what is different here? So here I'm only showing the parameters that correspond to the dip in the light curve, but I'm forgetting about the parameters that show you, the amplitude of the flux of your star and the slope of the flux of your star. So in the real data, there's no slope and there's no amplitude. So in the model that generated this data, actually here, this is 0, and there is no slope. And so the slope that we think we see here is just a random realization of this very complex covariance matrix. It means that, like points in this range are all correlated together. That's why they all seem to be below 0. And all these ones seem to be above 0. This is because they're all correlated together. But in fact, the mean here is 0. And there is no slope. So what we're saying is that we have assumed a model with an additional few parameters that we're going to call nuisance parameters that actually is not the right or not the true model. And that means that we'll get this type of thing, or this type of thing can happen because, we analyze data with a model that is not the same as the real model. And so if I do this last plot, where now I overplot the true model in black here, the mean of our posterior, so the values that are actually the most likely from my MCMC, so the one that are at the center of those contours in red, and the data points and samples from the posterior, I get a picture like this. So what I can see here is that the mean from my posterior probability actually fits the data better than the true model. Is that clear?
Yep.
So can you remind me, or I can look above, which was the parameter that was identifying the slope? Was it?
So the slopes, we're not showing them here.
Oh.
Let me just try to redo this one quickly.
In the contour plots.
Right. So those plots are like the amplitude of the dip, the location of the dip, and the width of this dip. But I can do this, and we can have a look at the entire chain. Right. And so now we see those two additional parameters at the beginning. The first one controls the slope of the background, and this one controls the amplitude, or the other way around, whatever. But we see that there is, a lot of uncertainties on those values, and these, you can think of them as reasons parameters that we don't actually, care about, because all we want is characterizing the transient event. And so when we look at just this portion here, we're just marginalizing over all of those.
Okay.
Okay. And yeah, so the final plot from this notebook is this one. And the main takeaway here is that now that we have included the proper covariance matrix, we have much wider uncertainties on the parameters, but there are also better uncertainties. You have a higher accuracy because the real value is closer to the center, or is actually, probable under your posterior. But it's still not perfect because our model has more parameters than the true model. And so it has more degrees of freedom, and it finds way to fit the data a little bit better. And in doing so, it actually finds parameters that are not the real value parameters. Okay, so I'm going to stop here and open to any questions that you guys may have.